All right, this is part 2 of your final exam review for this year, 2023. So let's start with number 36. You have to calculate the heat needed to raise 15.6 grams of water from 5 degrees Celsius to 37 degrees Celsius if the specific heat of water is 4.14 joules per grams per degree C. Okay, your equation that you're using to calculate heat, Q equals mc delta T, where m is your mass, C is your specific heat, and your delta T is your temperature change. And so for your temperature change, this is your T final, this is your T initial. And so delta T is always going to be T final minus T initial. And so that would be 37 minus 5, which is going to equal 32. So now we can plug all our numbers into the equation. 15.6 times 4.184 times 32, and that is going to give me an answer when I multiply all that together, 2088.7 joules. Energy or heat is going to be in joules. Number 37, they're asking you to draw and label an exothermic graph. So here we go. Draw our energy increasing going from top to bottom. Our reaction goes this way. And so we start with a certain amount of energy here. The reaction runs, and then it loses energy as it goes. And that's what an exothermic reaction does. It gives off heat. And so we did just say that this was at, so let's say 80 joules. And down over here, if we go this way, it's at, let's just say 40 joules. So it did lose heat. All right, that's an exothermic graph. An endothermic graph, the reaction absorbs heat. And so let's see where that's at. Oh, it's at the bottom here. Endothermic. Here we go. So it's going to absorb heat. So there's our energy. Our reaction runs this way. We start with a certain amount of energy. Let's say it's 80 joules here. And the reaction runs. And it absorbs energy. And if you go all the way across, let's just assume it's somewhere around 100 joules. So it absorbed heat. That's what that graph looks like. Partial pressures. This is Dalton's law of partial pressures. Here's the equation. What is the partial pressure of hydrogen gas in a mixture of hydrogen and helium if the total pressure is 0.236 atmospheres and the partial pressure of helium is 0.152 atmospheres? So the law looks like this. P total equals P1 plus P2 plus P3, and so on and so on and so on. So the total was 0.236, and helium's partial pressure was 0.152, and we had to find what hydrogen's was, the partial pressure of hydrogen. So I'm going to put hydrogen right there. So that means we're going to subtract. We're going to subtract 1.52 from 2.36, and when we do that, we get 0.084 atmospheres for the hydrogen gas, and that would be our answer. Number 39, the pressure of a sample of helium in a 1 liter container is 0.988 atmospheres. What is the new pressure if the sample is placed in a 2 liter container? Well, you are given an initial volume, you are given an initial pressure, and thirdly, you were given another volume. There's your V2. So the law, according to your reference materials that you have, P1 times V1 equals P2 times V2. And so we're really trying to find P2. We're looking for the new pressure. So when we rearrange this equation, P2 is going to equal P1 times V1 divided by V2. And that's going to be 0.988 times 1 divided by 2. And so if we solve for that, we have 0.494 atmospheres. All right. Listing the postulates of the kinetic molecular theory. Which postulate accounts for the fact that gases can be greatly compressed? Well, so particles of a gas in constant random motion That's 1. Volume of a gas, of the gases, is 0, pretty much. That means they're far apart from each other. Molecules are far apart from each other. Particles are. Third one is that particles exert no force on each other. And number 4, perfectly elastic collisions, meaning they don't lose energy when they bump into walls, each other. Just keep on bouncing, bouncing, and bouncing. Number 5, the kinetic energy of the particles is proportional to the temperature. So the higher the temperature, the greater the kinetic energy. The lower the temperature, the lower the kinetic energy of those particles. So the one that says gases can be greatly compressed would be number 2 here, because gases are far apart. There's literally no volume to them. Periodic trend showing the radius. Okay, periodic table showing the trend for radius, atomic radius. Well, I'm not going to draw the table. What I can tell you is this. For atomic radius, as you go down a group, okay, the periods increase, and each period represents an energy level. So atomic radius increases as you go down the periodic table, and as you go across the periodic table, it decreases. And the reason for that is the atomic number increases, and the atomic number is the number of protons in the nucleus of an atom. So the greater, the more the number of protons, meaning they have more pulling power in that nucleus. And essentially what happens is that it's pulling those electrons toward the nucleus and shrinking the diameter of that nucleus, of that atom, okay, the radius of that thing. So it increases as you go down the periodic table and decreases going across. That means there's more proton pulling power. You can get those electrons pulled closer to you. How are ionic compounds named? Well, you name the cation first, and then the anion name next. But instead of writing the entire anion name, we add IDE on the end. For example, we have this one right here, the common one we always use. Na is sodium, so you just write the name of the cation. And then Cl is chlorine, but instead of writing chlorine, we're going to add IDE on the end and write chloride, sodium chloride. Okay. Lithium sulfide. Well, lithium is Li, and that's got a 1+ charge. Sulfur is S, and that's got a 2+ charge. You want to balance those charges because the ionic compound has to have a net charge of 0. So the way we can do that is we need to add another lithium here with another 1+ charge. As we do that, 2 1+s, oops, let me erase that. The sulfur has a 2- charge. That's a mistake. There we go, 2- charge. All right, so now that we have 2 pluses and we have 2 minuses, that gives me a neutral atom, neutral compound. So now it's written as Li2S, right? Sodium oxide, same kind of idea. Sodium is Na, and that has a 1+ charge. Oxygen has a 2- charge. We need another sodium to balance that out. So we have 2 sodiums here. That would be, well, hold on a second. I screwed up with this. There we go. Again. Na2 because of 2 sodiums, and then just the O, Na2O. That would be the answer. Polyatomic compounds are named by combining the cation name with the anion, name of the polyatomic ion. Okay. So make sure that you have the cation name and then the anion name, the polyatomic ion, just put them together. So we have aluminum acetate. Here's an example of that. Aluminum is a 3+ charge. Acetate is C2H3O2, and that is a 1- charge. So you need to have 3 acetates. You need 3 of those acetates to equal the charge of 1 aluminum. So in effect, your new compound becomes AlC2H3O2 3. Oops, 3. We have 3 of those. Okay. Calcium nitrate. Calcium is a 2+ charge. Nitrate is a 1- charge. You need to have 2 nitrates to balance out the calcium, and that turns out to be CaNO3, 2. Put parentheses around that. So there's your 2 answers for that one. Okay. Covalent compounds. You write the name of the element for the cation. Well, no cation for the element, because it's not an ionic compound. It's 2 covalent, 2 nonmetals here, so it's covalent. So you need to use the proper prefixes. Okay, and the prefixes are for these. We have 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. Okay, so you need to know those. That's important. So we have down here phosphorus, tetraphosphorus, pentachloride. Phosphorus is a P, chloride is going to be Cl. Tetra is 4, penta is 5, so that would be P4Cl5. The prefix tetra, when you write it as a number, actually goes after the symbol, and that becomes a subscript. We have diphosphorus, that's P, and that's going to be a 2. Decoxide, oxygen, and that's going to be 10. That's going to be P2O10. That's how we write that. Thermal equilibrium. That's easy. Thermal equilibrium. Where are we at? Oh, I missed some, didn't I? Yeah. 3 examples of heat transfer by radiation. The sun, heat felt by the fire. Okay, those are 2 examples. Heat from a hot burner on a stove. And there are others, but those are 3. Transfer by convection, boiling water, hair dryer blowing, and rising and cooling air. Those are 3 examples of convection. Now we can get to number 47, which thermal equilibrium. When there is no net flow of thermal energy in a system. So let's just taking this example here. When you have ice melting, it's going to continue to melt, and it'll stop melting and the temperature won't change anymore when it's totally melted. Okay, so that's an example of thermal equilibrium. The temperature of the air and the temperature of the melted ice, the water, is the same. A conductor can transfer heat easily. An insulator does not transfer heat easily. Okay, wood is an insulator, metal is a conductor. So we'll just put a little example, metal. We'll put wood down here. Those are insulators. Heat always travels from, let's change that, the hot object to the cool object. We're going to draw Lewis dot structures here. We're not going to include those down here. So what we have to do in drawing Lewis dot structures, we have to look at the valence electrons. Okay? And so hydrogen is in group 1. Hydrogen is 1 valence electron. Okay? And there are 2 of them here. So let's just show 2 of them. And as we do this, as you bond 2 hydrogens together, they're going to share their electrons. So you put 2 dots in between those 2, and they're both sharing them. Okay? So that would be the Lewis dot structure for H2. Cl2, 2 chlorines. Chlorine is in group 7, so it's 7 valence electrons. So let's draw 2 chlorines bonding together. So you need a total of 14, because 7 times 2 is 14. So there's 14 total VEs, valence electrons. So let's draw a bond right in the middle of those 2. So we need to have a total of 14, and we want to create an octet around each one. Octet meaning 8 electrons. Remember, they're sharing them because this is covalent bonding. This is not ionic bonding when there's a transfer of electrons. So we make sure we have 8 around each one. Well, there's 8 around that first Cl, chlorine. Here's 8 around the second one. If you look at that, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. They are sharing, and so this would be the Lewis dot structure for Cl2. And that is your exam. Study this, and good luck to all of you.